Okay, this is the first example for section 12.7. We are talking about here to solving the problem using tangential normal coordinates. Because we have a car traveling along a road with a speed of 20 s. So we are giving the speed in terms of the path. So if you look at this s, I'm going to put it in pink because I wrote this in pink, is the velocity is given in terms of that path that car is traveling along the road. And we are given also the radius of curvature of the road. So it's like you are traveling around a highway and then you take an exit and then that road has a curvature. And then we need to know that we don't have actually only tangential acceleration, but we also have normal acceleration. So we want to find the magnitude of the acceleration at s equals 10 meters. So when it has already covered 10 meters of that curve. This is the solution. We know that the acceleration has two components. Have a component in the tangential component, let's call it ut, the unit vector in tangential direction, plus a un. So I just call those vectors the unit vectors in tangential direction and u in normal direction. So if we want to draw those coordinate systems, we'll have to draw a tangential direction and a normal direction. Those two are perpendicular and represent our coordinate system, which is tangential normal system. Our velocity is always tangent to the path with this s. So our velocity, that velocity that is given, is always tangential to the path. However, the acceleration has two components. The tangential component is the derivative respect to time of the velocity, and the normal component we know that is the velocity squared, the radius of curvature of our path. So let's find out first our tangential acceleration, which is the derivative of the velocity. So this is derivative respect to time. Our velocity is given in terms of the path. So we want to derive something, an expression that is given in terms of s, but we want to derive with respect of t. So as we have done previously, we have to use our chain rule, right? So that will be the derivative of s, the velocity, times the derivative of s times time. So we have the derivative of the velocity with respect to our path and our path respect to time. It's very important to remember our formulas. We know that the velocity have a vector formulation, or we can have a scalar formulation. In a scalar formulation, we can derive our path respect to time. That's a scalar formulation. So actually, this term right here is our velocity. So we have the velocity times the velocity respect to the path. And that velocity will be that expression right here, 2s, and the derivative of the velocity respect to s will be, let me write it down so that it's very clear. So the derivative of 2s respect to s is 2. So at the end, I will have 2 times 2s, 2s times 2, which is 4s. For the value that we are being asked, which is 10 meters, so for s equals 10 meters, we have that our tangent acceleration is 4 times 10 will be 40, and our units are meters, so it will be meters over second square. That's our tangent acceleration. Now we have to find our normal acceleration. So 40 meters per second is the acceleration the car will feel in the tangent direction, but then we have to find the normal acceleration, which will be the velocity squared over the radius of curvature. We don't have to derive anything. It depends only in the velocity. So that's why when you take a curve with a very high speed, even though if that speed is constant, that you maybe get a tangent acceleration equals to 0, so you're not accelerating in tangent direction, you feel a very high acceleration in the normal acceleration, because the normal acceleration depends only in the velocity. So if we have this, will be s squared over our radius of curvature. That's the expression for our normal acceleration. For s equals 10 meters, we can have that the normal acceleration will be 20 squared over 50. And that's equals to 8 meters over second squared. So there we found our normal acceleration. So we have our tangent acceleration and our normal acceleration. If we want to find the magnitude of the acceleration, the magnitude of the acceleration will be the square root of the tangent acceleration plus the normal acceleration to the square. To the square root of 40 square plus 8 square. Now we got that the magnitude of our acceleration is 40.8 meters over second square. This is in magnitude. If we like to write it as a vector, we can write it as 40 in tangent plus 8 in normal direction. We could even, if we are asked or we like to, find that acceleration in other coordinate system. I found it in this coordinate system, where this is normal and this is tangent. But you could maybe think that you want to find it in x and y, then you will have to find that angle, this angle, which will be the same as this one. But that we are not being asked to do so. And usually you probably don't care about the acceleration in x and y direction. It doesn't mean as much as the acceleration in the tangent and the normal direction, because that's probably the acceleration that the driver is feeling, that is feeling a normal acceleration depending on the velocity that he takes the curve.